Okay, so this trick is all about dimensional reduction. Okay, so the first point is that neural networks really don't work well with large dimensional inputs. Okay, so in fact they're happier. Maybe the reverse is that if your inputs are larger than 100 in size, then you've got to worry about dimensional, what's it called, the curse of dimensionality. I'm sure you've heard of that before, right? But frankly speaking, neural networks like this, are better off when your dimensions are smaller. So the idea here is that you want to reduce the dimensions of your input vector using some kind of compression, decompression subnet. Okay, so I'll explain what that means. Um, you have your inputs, you have this compression, so it narrows down, and then it decompresses, so it goes up. Okay, and you want to train the network so that your X reconstructed must match your input X, obviously, but you don't use the reconstructed vector. Instead, you tap the center part of the network, the reduced vector, and you use that instead as your input into your feed-forward network. Okay, so this is a distinct subnet that you use just to reduce the dimensions of your data. Okay, now in our case, if you recall, we have, I think, 33 inputs. Okay, that's the difference plus the momentum, and then what is it called, the force. All of that is just 33. So it's not a big dimensional vector, but even then you can actually see some improvements if you do some dimensional reduction. Okay, but it's tricky, and you need to know how to do it correctly. Okay, so the first thing is this: keep it simple. Is that 3 layers is more than enough. Okay, so don't go crazy and try to use multiple layers. 3 layers is more than enough. Okay, and use 10H because it saturates at both ends, and you want that. Um, and the compression factor, in other words, from the base to the middle part, how much should you compress? Well, you can start with 2, or you can start to scan. You can scan a few different numbers and see which gives you a good result. Okay, and you can actually easily, for most time series, you can just train these models up. In fact, you probably want to train them up simultaneously with the rest of your network with a separate loss, obviously. Okay. All right. So I'm going to show you how to do this. This is a little more complicated, but not that hard. And I think this example also shows interactions between different things. These techniques are not all independent of each other. They actually do have interactions, and you have to be just a bit more careful about how they interact, right? So let me open up the config. Okay. The main. The pre is all the same. I'm not changed the pre at all in my network. Okay. So you can see here, my network now is starting to grow. Okay. Right, so this is the main part of my network, right? The network word itself. Now, I previously had just the scaling followed by the 4 layers and then the final LC layer. Now I'm introducing the bottleneck just after scaling. So it's scaling first and then bottleneck second, okay? So remember, in Smojo, everything is in order. So this is why, well, it matches what you would think of as a transformation. Whereas in Python, or let's say in Java, it will be bottleneck bracket scaling, not like this, right? Okay, so you do the scaling first, and then you do the bottleneck. Okay. Now, my main network, the perceptrons are ReLU based, and they have a dropout. Previously, I used a dropout of 0.1, but now the dropouts need to change, and I explain why in shortly. Now, my scaling before had that diagonal thing, but it also had a 10H. Now, I've removed the 10H because the bottleneck already has a 10H. Okay? So I don't use a 10H here and saturate too early. I've removed that, and it's up here right now. right? And this is my dimensional reduction subnet. The perceptrons now are 10H based, so it's just the inner product with a 10H after that, okay? And this needs a little explanation. So I've got the input that comes in from the bottleneck. So this is the input. Anything in purple that you see here is a comment. Okay, so this is not, this part here is not a method signature. This is just a comment for me to know what the inputs are and what the outputs are. Okay, this is a binding which accepts it, which calls the input to bottleneck as XS, which is the input layer. And here, what I'm doing is that I'm creating the first part of the bottleneck, okay, the base layer. Then here I'm doing the second. So you probably can't see this, but highlighted. But let me make it bigger. Move this off. Okay. So here it's again a layer of perceptrons, but the size is the input layer divided by the bottleneck size. Now the bottleneck size I've used is actually 4. What I did previously was to scan a few different values. So in AutoCAD, sorry, you can actually scan stuff by giving them multiple values. So in this case, the bottleneck could be 1.5, 2, 4, or 8. Now, to save you the trouble of doing all that stuff, I've done it already. And the best answer, at least for this configuration, is size 4. Now, this will definitely vary or be different according to your application. So you must scan the appropriate size for your bottleneck so that it's not too small and not too wide. Too wide, you lose the benefits of the bottleneck. Too small, then it doesn't train properly because you lost too much information, right? Okay. Now, the dropouts also need to change. Why? Because previously, for all the previous experiments, my dropout was 0.1. And that's because previously, the size of my inputs was 33. Now, the size of my inputs is 4 times smaller than that. So it's roughly about 10-ish. Okay. So it's much smaller than before. And so because of that, I've got a lot of neurons which I don't need anymore. I need to cause dropout. Otherwise, I get over training. Okay, overfitting. So when you use a bottleneck, be sure to actually also scan for a good dropout. Now, this should be obvious. Which direction you should go should be obvious. It should become larger. And how much larger is really the question. Okay. And I'll also increase my repeats to 60 because the more of these techniques you use, the more unlikely it is for you to get a good result. So you need to work a bit harder. I've only just doubled the amount of tries. Okay. So let's look at the losses. Okay, so you can see there's a lot of variation here, and because that's the bottleneck is introducing a lot more fuzz into your training, a lot more variability in your training, right? And also because of the dropouts have increased. So previously, when the dropouts are lower, you get a narrower band. When dropouts are higher, obviously you get a wider, higher band for your training, right? And you can see some do well and they're obscured by the blue, so you can't really see it so clearly. And of course, a lot of them will just fail. In fact, your main body is not doing too well here. It's all the way up there. Okay. Now, this is the losses not for the main network, but for the reconstruction network. So you need to check this graph to make sure that it's actually nice and smooth and going down. So now here, I've got my blues higher than my reds, which might seem unusual, but not really, because my blue, my training data set is very large. And obviously what this means is that the input data set can be easily reconstructed. Okay, so you want to see this going down, but you see there will always be a small amount of error, reconstruction error, and this is what you pay for when you use a bottleneck layer. Now, because this is such a mess, and you can't see the all 60 configs, there's too many of them, and they're obscured by the blue here. I've just plotted out just the best config here. And so the best config here, this is a good result, right? So you've got, your blues going out there, and you've got your red line there, and it's actually reduced below. And let's see the how far you are from the main body. Not too far. 2.2 is not that bad, or 2.3 really is not that bad. Okay, which means that this result, if you work a bit harder, you might be able to reproduce it. Okay, so this tells us that using the bottleneck is good, but we only want to eyeball the predictions just to make sure, and to look at the lag plots. Okay, so here you can see, if you notice carefully, there's a slight shift towards the right. So it looks like it's a bit laggy, the training part, and that's natural because you've doubled the dropout values from 0.1 to 0.2. So typically what happens is that when you increase the dropouts, the training error goes up, but the test error goes down. Okay, up to a certain point, obviously, right? When they start to meet, then both start to go up. Okay, because that's just too much noise in the training itself. So here you can see, yeah, it's a lot better than before. It's really faithfully followed this thing down. It's actually easily forecasting this. There's a lot of oscillations that's to be expected. And then you've got the spike here modeled correctly, this trough here correctly as well. Not a bad result all in all. Okay. And the lags, well, it doesn't tell you a great story, but because this is such a short test sample, I would actually be a little skeptical of this, because that's why I need to eyeball this thing a bit more. Okay, so if your data sets are longer, then trust the graphs like this, like these lag graphs. They are much better at actually looking at that and giving you the information you need. Okay, but here, even so, we've got at least some semblance of it out here, I guess. Okay,